In this second film about electrostatics, we'll be looking at more important applications, more examples of physics in action. First, a demonstration. Electrostatic charge can be built up by the friction of a liquid against a solid. This pump can pump paraffin around a closed circuit of piping. Here the paraffin passes over a nylon surface. These are actually nylon pan scrubs. From there it passes into a copper container. And it's then recirculated around the back to the pump again. We connect the copper container and a metal collar in contact with the paraffin just before the nylon to the voltmeter in the middle. Then switch on. As it rushes over the nylon, the paraffin gains an electrostatic charge, which it transfers to the copper collecting vessel. A potential difference builds up. In a short time, there's a potential difference between the paraffin from the pump and the copper container of over 1.5 kilovolts, over 1,500 volts. If we now electrically connect the 2 points across which there is this potential difference, the potential drops to zero. What's the importance of this? Well, it's important wherever non-conducting and inflammable liquids like paraffin have to be pumped rapidly from one container to another. So it's important where, for example, aviation fuel is handled, as at airports. A light plane is to be refueled. Before any fuel is pumped from the tanker to the fuel tanks in the plane, a line of cable is run out. It's called a bonding line. It's attached to some clean metal part of the plane so that there's now electrical connection between plane and tanker. Now the fuel lines run out. Another cable connecting the nozzle with the plane. And fuel can be pumped aboard. It's necessary to pump the fuel rapidly, or the whole process would take a long time, especially with the big jets. This means that there's the possibility of electrical charge building up in the plane's fuel tank. If a spark occurred, the effect would be disastrous. From the demonstration you saw earlier, can you see how the bonding line stops this happening? The job's completed, quickly and safely. There's perhaps less chance of a spark causing an explosion on a wet day like this, but even so, this procedure's always followed at every airport. It's just the same with the big jets. Here's one being pushed into position for refueling. She'll take aboard much more fuel than that light plane. The bonding line again. And there's a special connection point on these big planes. When fuel gushes through the pipeline into the plane's tanks, there's always the risk of a big electrostatic charge building up. The bonding line prevents this. It's part of the safety procedures, as important on the ground where planes and inflammable fuel are handled as in the air. Physics applied to making air travel safer. Friction can be used deliberately to produce electrostatic charge in the laboratory. You've probably seen this kind of machine, a Van der Graaf generator, which can be used to demonstrate all kinds of electrostatic effects. For example, let's put these strands of silk fixed to a metal base on top of the machine. Now we'll start it up. The belt carries charge to the top, where it's spread out over the outside of the metal sphere. At the same time, the separate threads of silk become charged. They all get the same kind of charge, and if you remember that like charges repel each other, you'll understand why this happens. Now let's discharge the sphere by bringing near this smaller Earth sphere. A spark passes and the silk threads collapse. If everything's made very dry and it's run for long enough, the machine can build up a potential of thousands of volts, sufficient to spark across this air gap to the Earth's sphere. Let's take a look inside this Van der Graaf generator. We must switch it off and discharge it first, or we'll get an unpleasant shock. Inside the base, the continuous belt runs just above a metal wire spiral. This can be given an electrical charge, which it then sprays onto the belt so that it's carried upwards. Or you can just simply let the machine run in very dry conditions, and there's enough friction between the moving parts to create charge, which is carried upwards by the belt. Let's look at the top. Here there's a similar device. Charge brought up on the belt now passes from it to the wire spiral and spreads out over the surface of the sphere. Now this is a laboratory demonstration model capable of building up a charge of thousands of volts under good conditions. There are much bigger machines. Look at this belt of a Van der Graaf generator. And here's the machine it's used on. This one can produce a potential of 6 million volts, so high that it has to be run inside a tall metal tank. You can see the top of this tank being taken off. The tank's filled with a gas called sulfur hexafluoride, a very good insulator. In air, great sparks would discharge it before so high a potential could be built up. The belt runs inside these rings. Here's the top. Inside, it looks like this. It's more complicated than the small lab machine, but the principle's the same. Here's the top of the belt running over a big pulley, and charge brought up from below is taken off it by a strip of metal gauze, which rubs against it. You can see the gauze brushing against the belt. Here's the rest of the tank coming off, so that we can see the bottom of the machine. Looking up it, you get a good idea of its size. At the bottom, a gauze brushes charge onto the belt so that it can be carried up to the top. What are such enormous machines used for? Here's a sectional diagram. There's the tank of sulfur hexafluoride gas with the moving belt inside it. The very high positive potential produced at the top is used to repel positive ions, charged atoms, of various elements down a tube, so that they reach the bottom travelling with a very high velocity. Here we are underneath the generator. Certain of those positive ions, travelling very fast, are steered around this corner by a big electromagnet. They pass along this horizontal tube, which will bring them to focus on a target of some kind at the end. The target's jiggled about mechanically. If the fast particles kept striking it in one place, it would melt, and water's used to cool it. Such experiments show how different metals, say, will behave inside nuclear reactors and so on, and they hope physicists understand the structure of the atom, what matter is made of, and why it behaves as it does. Bigger and even more powerful Van de Graaff generators are being designed and built using the principles of electrostatics to investigate the structure of matter and to provide engineers working in the nuclear industry with the sort of information they need as they develop their exciting new products and processes. Back to the laboratory for some more experiments in electrostatics. One terminal of this battery can be connected using this lead to a metal plate on the left there. The other terminal can be connected through a very sensitive galvanometer to the other plate. There's air, of course, between the two plates, which make up what's called a capacitor. Let's start with the two plates very close together, but not touching. If we connect them to the battery, the needle shows that a current flows, but fairly quickly dies away. The zero is at the center of the scale. Here's what happens. The capacitor's at the top and the battery at the bottom. When we connect the battery to the plates, it acts as an electron pump, pulling electrons off the right-hand plate and making it, therefore, positive, and pumping them onto the left-hand plate, which becomes negative. This process continues, the right-hand plate gaining a bigger and bigger positive charge, and the left-hand plate a bigger and bigger negative charge. This goes on until the potential difference across the plates of the capacitor equals the EMF of the battery. No more current flows, and we say that the capacitor's now fully charged. We now connect the two plates electrically by touching the two leads together. A current flows in the opposite direction from before and quickly dies away. Look at the diagram again. When we connect the two wires, electrons flow back from the left hand to the right hand plate. Current flows in the opposite direction from before until all the charge has gone from the plates. We call this discharging the capacitor. Watch it again. Now the capacitor's fully charged and the current stops. Connect the plates and the current flows in the opposite direction, dying away as the capacitor discharges. Now let's move the plates further apart. If we now repeat the experiment, the same thing happens, but there is a difference. Watch. The current passes for a much shorter time. When the plates are further apart, we say that the capacitance is smaller. The battery pumps electrons round as before, but the plates can now hold less charge and the current stops flowing much sooner. Let's discharge the capacitor. Once again, current flows in the reverse direction, but again it very quickly dies away. You can see that the current must die away more quickly because there's less charge on the plates. They very quickly become neutral again. Watch it again in the lab. Now let's connect the battery permanently to the two plates of the capacitor. Current flows until the capacitor is fully charged. Suppose, once this has happened, we deliberately change the capacitance of the capacitor by moving one plate in and out. Then the charge on the plates will either build up as capacitance increases or be reduced when it decreases. We'll get current flowing in one direction or the other as the capacitance changes. We're changing static electricity into current electricity. Here's the capacitor again, with the plates very close together. It then has a high capacitance, as we saw earlier. When it's charging, the current passes for 2 or 3 seconds. And when we discharge it, again, a current flows for several seconds. There's another way in which its capacitance can be altered, not by moving the plates further apart, but by making the area of overlap between them smaller, like this. It's as if the capacitor now has smaller plates. It now takes much less time to charge up. Its capacitance is smaller. And the current dies away as quickly when we discharge it. Capacitors are made whose plates can be moved relative to each other so that we have what's called a variable capacitor. This is one of a kind sometimes used in radio transmitters and receivers. You can see how the plates, there are several pairs combined in the one instrument, can be made to overlap to a greater or lesser extent by turning the knob. This makes the capacitance vary, and it's a way in which radio circuits are tuned. There are variable capacitors in radio sets, for instance. The tuning knob alters the capacitance, and the radio then picks up stations on different wavelengths. In this film, we've been looking mainly at static electricity and seeing how it can be generated. The next film is the first of 2 which demonstrates how electric current can be generated in the laboratory and in the giant power stations which provide the electrical energy on which modern life so much depends.